Hello again. This is video lecture 23.2, where we introduce the topic of this chapter, Gauss's Law. So the reading, if you wish to get more detail, is chapter 23, section 2. And here's a statement of Gauss's law, first in words. The total electric flux through a closed surface is proportional to the total charge inside. We often say that the total charge enclosed by that surface. So here it is in symbols. Phi electric is proportional to Q enclosed. ENC stands for enclosed. Now, we spent the last video lecture and the previous class learning how to calculate electric flux through a surface, including a closed surface. So that's still going to be all required. And we're still going to be using those ideas. But what Gauss is telling us is that once you know the phi electric, the electric flux through a closed surface, that's telling you something about the total amount of electric charge inside that surface. And it's only telling you about the total charge inside the surface. Okay? Turns out that it's only the net charge inside a closed surface that contributes to the electric flux through that surface. But then the big question is, what's the proportionality constant between phi electric and Q enclosed? Anytime you have two things that are proportional, you can just introduce some proportionality constant and have an equality between them. So I'll call that constant big C for now. But then the million-dollar question is, what's the value of that constant? I'm going to give you what's called a plausibility argument for it. If you want a proof, you'll have to wait till Physics 360, electricity and magnetism. But I'm going to give you a plausibility argument and then tell you to trust me from there on. I'm going to calculate that proportionality constant, the thing I'm calling for the moment big C, by looking at a specific situation, not a general situation, namely a positive point particle with charge Q, sitting all by itself, alone, in space. No other charges around at all. And I'm going to apply Gauss's law to a Gaussian surface shaped like a sphere, with the charge at the very center of the inside. Might as well. That's like the best choice to make to take advantage of what's called the symmetry of this situation. Because I know that for a positively charged point particle, the electric field that it creates in all of space around it just points radially away at any given point from the charge. Okay, so now the problem with two-dimensional drawings representing surfaces in 3 dimensions is you have to remember that the drawing that you're seeing isn't the whole story. So we're drawing the Gaussian surface in this picture, trying to do it here. It looks like it's a circle. But what that really is saying is that it's the surface of a sphere, like a blown up balloon that's been tied off. Okay? So that's the surface we're going to pick. A sphere with the charge at the center. Then we know at any point on this Gaussian surface, the electric field vector at that point points radially away from the charge. Like there, I just drew the electric field to the right for that little region of the sphere. What about the little region of the sphere that's directly below the charge? Then the electric field points straight down. What about the little region of the sphere that's directly to the left of the charge? Then the electric field points due left. What about the region of the sphere that points directly above the charge? Then the electric field points straight up. And you can keep going, right? You can imagine the region of the sphere that's out here on this diagonal. Then the electric field points like that. Always radially away from the charge, which we chose to be at the center of the sphere. Now what I want to do is, using all the symmetry I've got going for me between the electric field and the Gaussian surface, I want to get a symbolic expression for the electric flux through the surface. The surface, again, is what I've kind of drawn with black color. And the electric field vectors, some of them, I've drawn with purple arrows, and I think it's pretty clear that there are purple arrows piercing through the black surface. There is electric flux through the Gaussian surface. I want a symbolic expression for it. There's the starting point. The integral E dot dA over our Gaussian surface. Note I put also a circle sign. Draw a little circle on the integral symbol. That's a signal to the reader that the surface we're integrating over is closed. Now let me come over here to the side and say a little bit about E dot dA, what you could call the integrand, just that. Well, let's just imagine one little patch. How about the one over here on the right? This one. Now there's a little area patch right here. It's a little bit hard to see because you're looking at it kind of edge on. It's a little patch of area on the surface of the sphere. Which way would its dA point? Can you visualize that for that little patch? Think about that for a moment. Pause the video if you don't want to feel rushed, okay? Think about it. Which way does the little area vector dA arrow for that little patch that I'm seeing drawn in red and I'm seeing edge on, which way does it point? Okay, did you say the little dA points perpendicular to the surface there and outward? Right, like that. That makes sense? So come back over here and do the E dot dA for that little patch. It's magnitude E, magnitude dA, times the cosine of the angle between the E and the dA. Well, there they are over there. Right there. The E and the dA have a common tail and they're both pointing in the same direction, right? So that's the cosine of 0 degrees. And the cosine of 0 degrees is 1. So this expression just reduces to magnitude of E times the magnitude of dA for that little patch. Now, I picked that one patch there on the right side of the sphere, but you could have done the same thinking for the patch over here on the left side. There's the little area patch. There's the little dA. Well, look at that. The E and the dA are again parallel. Or what about the little patch at the top of the sphere at the North Pole? There's the dA for that little patch. Oh, but again, the E and the dA are parallel. What about this little patch over here on the side? Oh, again, the E and the dA are parallel. For every patch, the E and the dA are parallel. And so symbolically, that E dot dA looks like that. Okay? And so that's what goes inside the integral. So what I really have inside the integral is that symbolic expression. Here comes the next big, amazing thing, all because of the choice of Gaussian surface. The wise choice of Gaussian surface makes all the difference. Since I chose a sphere for my Gaussian surface, with the particle at the center, it must be true that every point on the Gaussian surface is the same distance from the center, namely, whatever the radius big R that the sphere has. True? And remember, we already learned in chapter 22 how to calculate the electric field produced by a point charge. And the formula is Q over 4 pi epsilon 0 R squared. Q over 4 pi epsilon 0 distance from the charge squared. But every little patch of area, dA, on the surface is the same distance R from the same charge Q. Yes? So every little patch has the same E magnitude. That's the key thing. Same for every patch on the Gaussian surface. What do you get to do with some part of an integrand that's the same constant during an integral? You get to bring it out front. That's how I get to this line right here. For the electric flux through this Gaussian surface, bring the magnitude of E out front, and then what is that weird-looking integral? Don't overthink it. It's add up over the closed surface all the little areas of all the little patches that make up the surface. But wait, that is not hard to conceptualize what that will be. If I add up over the spherical surface all the areas of all the little patches that make up the surface, I will just have the surface area of a sphere. Now, basic geometry is something that physicists and engineers need to just have in their head. There is a well-known formula for the surface area of a sphere. I'm not talking about an area of a circle, I'm talking about the surface area of a sphere. And we're going to use it a lot. It is 4 times pi times the radius squared. 4 times pi times the radius squared. So here is my symbolic expression for the electric flux through the Gaussian surface. The magnitude of the electric field, which is the same everywhere on the surface, times the total surface area, 4 pi big R squared. Okay, it's really, really important for understanding this chapter that you're with me at this point, that you follow the steps that got me to this point. Because we're going to do this kind of thinking from now on in this chapter and following chapters. Now, here's one thing I am going to do that's going to be a bit different later on in the chapter. I am going to use the fact that in this particular situation, I already know the formula for E magnitude. It's the electric field of a point charge. E magnitude is Q over 4 pi epsilon 0 R squared, where the R is the distance that you are from the charge. In that case, that's big R. So I'm going to substitute that expression right there, that whole thing, for the E magnitude. I'll come over here and calculate it symbolically so that you can see. Okay, so for E magnitude, valid everywhere on the surface of the sphere, we have Q over 4 pi epsilon 0 R squared. Remember, in the flux formula, I multiply that by 4 pi R squared. So let's see, there's a 4 upstairs and downstairs. There's a pi upstairs and downstairs. There's an R squared upstairs and downstairs. All that's left upstairs is the Q, and all that's left downstairs is the epsilon 0. So my final expression for the electric flux in this case is Q over epsilon 0. Oh, but wait a minute. The Q I have here in this particular case, is it not the total charge inside the Gaussian surface? It is, isn't it? So that Q there is actually Q enclosed. And so what I've really shown you is what that proportionality constant is, right? So what I've got for my special case is that. Now compare that with the formula I had above, and I see that the proportionality constant C is just 1 over epsilon 0. And so we get Gauss's law, valid in general, okay? Not just limited to a point particle at the center of a spherical surface, but absolutely general in electrostatics. Again, I'm just asking you to accept that fact, that it's generally true. I derived it for a special case. It is generally true. You want to see the general proof? You take Physics 360. Again, Gauss's law says in general that the electric flux through any closed mathematical surface is equal to the total charge inside that surface over epsilon 0. It's got to be charge inside. And here, by the way, is why we wrote way back in Coulomb's law for the electrostatic force between two charged particles. We wrote K, Q1, Q2 over R squared, but then we wrote K as 1 over 4 pi epsilon 0. And the question at the time was, well, why bother writing K as 1 over 4 pi epsilon 0? Now we know why. Because in writing it that way, we get Gauss's law with a simple form. Q enclosed over 4 pi epsilon 0. Otherwise, it'd be something like Q enclosed times 4 pi over K. And it's just simpler to write Gauss's law this way. And Gauss's law is more fundamental than Coulomb's law. And we'd rather have Gauss's law be a simpler expression than Coulomb's law. Okay? All right. Now let's remind ourselves of what these terms mean, because Gauss's law is a very straightforward equation to write, but we have to make sure we understand it. So where we have the expression phi electric, remember we mean the integral over a closed mathematical surface of E dot dA. That's what the phi electric symbol means. And the Q enclosed symbol means add up all the charges I that are inside, enclosed by the Gaussian surface. Add them up. It's got to be the net charge enclosed. Okay? And then divide the right-hand side by epsilon 0. So what I want to do now is start practicing right away, applying this. And I'm going to do that with some Wiley Plus animations. Okay? Okay. So, and also to do that, I'm going to need a little bit of room to write, and I'm going to have to go back and forth between the animations and my writing. So let's write down here the formula for Gauss's law so that we can remember it. And now let me transition to the first animation. And let's make sure we understand it. Okay, in this animation, we have a point particle with charge, positive charge. I don't know how much, but it's positive charge. It's sitting at the origin of an XYZ coordinate system, creating electric field vectors that point radially outward from it in all directions. Those arrows that you see represent the direction of the field at any given point, not the magnitude, by the way, because the arrows are all the same size, and that's not what the magnitude does. But at least they show that those arrows show the direction. The animation also shows in cross-section, 2D cross-section, a closed Gaussian surface, which right now is shaped like a sphere. Now it looks in the diagram like a kind of a dark red circle, but it really is a cross-sectional slice of a sphere, which is a closed surface completely surrounding this charge. Okay? And so if I want to think about the electric flux through that Gaussian surface, I see that there definitely is electric flux, because I've got electric field vectors piercing the Gaussian surface outward. In fact, over here at the edge, if I can hover over them, you'll see a black arrow and a brown arrow. The brown arrow represents the electric field right there at this little patch of surface, and the black arrow is the normal to the surface, called n hat. That'd be the direction of the dA for the little patch that's right on that surface there. Bottom line is the E is piercing the surface in the same direction as the n hat outward. And that's happening everywhere over the Gaussian surface. So we definitely have positive electric flux. Okay? In fact, the animation shows me what you get when you integrate E dot dA over that closed surface. And it's right there at the top of the picture. Do you see it? Phi sub E equals the integral over the closed surface of E dot dA, and it gives me a number. So I'm going to write down that number. That's the phi electric. 1.13 times 10 to the 5 Newton over Coulomb times meter squared. So here's my first question for you to think about. What is that Q of the charge that you see there? See the blue disk at the origin? That's a charge. How much charge is it in the SI unit of Coulomb? Do you see how you would answer it? Hint, Gauss's law. Sorry, I have to go back so you can see what I've been writing. Okay, I wrote Gauss's law. I just wrote down the value of the electric flux from the animation. There's my question. What is Q? Do you see how to get it? The answer is that the Q that's inside is the Q enclosed, right? It's inside. And the phi electric is a value, quantity I have a value for. So let's just take Gauss's law and solve it for Q enclosed. Q enclosed equals epsilon 0 times phi electric. And epsilon 0 is a known constant. So this is 8.85 times 10 to the minus 12 Coulomb squared over Newton meter squared. And I'm given the electric flux through our Gaussian surface, 1.13 times 10 to the 5 Newton meter squared per Coulomb. Well, let's see what happens here. We've got one factor of Coulomb cancels there. The Newton cancels the Newton. The meter squared cancels the meter squared. I will have units of coulombs. I have to go to my calculator to see what that gives. It gives 1 times 10 to the minus 6 coulombs. Or the way the physicist would write that, 1 microcoulomb. Okay, now we know how much charge that is. That's inside that Gaussian surface, 1 microcoulomb. And that won't change throughout this animation. Okay, here's what I'm going to do next. I'm going to go back to the picture. I'm going to, with that weird-looking slider object at the very top, I can move around the center of the Gaussian sphere. Right now the center is at the origin. Right? I can move it around with that slider up there. I'm going to move it around. I'm going to move the Gaussian sphere around a bit so that the particle is no longer at the center, but will still be inside the sphere. Question: what will be that electric flux number that you see at the top? Because it will automatically calculate the flux for the surface, the location of the surface. What will that number be for the electric flux? Pause the video, please. Think about that just a moment and then come back. Okay, let's move the Gaussian surface, sphere, off center. Oh, maybe over here. Oops, gotta get to the right place here. Here we go. See the center of the sphere is marked with the X, but the charge is still inside. Do you see the number up there for the flux? Didn't change. Why? Because the value of the flux must equal the total charge inside. And no matter where the charge is, if it's inside, it's inside. And the flux through the surface will be equal to Q over epsilon 0. Note that if I get the charge way off center like that, then the E and the dA at any given patch, like up here, well, they're not in a nice simple arrangement anymore. The E isn't perpendicular to the surface anymore. So actually trying to calculate the flux through the surface like this, by doing the integral of E dot dA, would be a nightmare. Absolute nightmare. But I don't need to do the actual integral of E dot dA. Gauss's law tells me what the answer will be. Q over epsilon 0, and the Q is still inside. Does that make sense? Okay, what will the flux to the Gaussian surface be, as represented there on the animation, if I move the surface, the center of the spherical Gaussian surface so that the charged particle is no longer inside? Think about that, pause the video, and then come back. Okay, let's move the center of the Gaussian sphere so that the charged particle is no longer inside, and then watch the result for that flux integral up there. Boom, look at that. Drop to 0. 0, 0, 0. As long as the charge is outside, the electric flux through it, through the surface, is 0. Now, how can that be, you're wondering? Because the electric field vectors are still there, right? See all the arrows pointing around? Okay, but when you've got an arrangement like I have it now, we know the electric flux has to be 0 because there's no Q enclosed. It must be the case that I have exactly an equal amount of positive flux contribution from electric field vectors piercing outward, like up here in the upper left, as negative flux contribution from electric field vectors piercing inward, such as happening down here in the lower right. And it is exactly balanced. The positive flux and the negative flux exactly balance out to a 0. That's pretty amazing, isn't it? But if I move the center so that it encloses the charge again, watch the flux will jump back up. Boom. 1.13 times 10 to the 5 Newton meter squared per Coulomb. Okay? All right, I want to do a little more practicing with a slightly more complicated situation. All right, now I've changed the animation. Now what I have are two charged particles, the red one and the blue one. And the sliders up there allow me to set the values of those charges. The red particle's charge, -1 microcoulomb. Blue particle's charge, +1 microcoulomb. The arrows represent the direction of the total electric field produced by the charges together throughout the xy plane. And then I have a spherical Gaussian surface currently centered at the origin. Now this one does not display the actual value of the electric flux through this Gaussian sphere, does it? So I'm going to ask you, what is the answer for the electric flux through this Gaussian surface? Pause the video, think about it, and then come back. Okay, now this is an interesting situation, isn't it? Because there are some regions, such as in the upper right area over here, you can see I've got the n hat, the black arrow, that's the dA direction. And then right there, hard to see it, there's the electric field vector going kind of downward and to the right, piercing inward. That'd be a negative contribution to the flux. I've definitely got piercings. I've got some places where the electric field pierces coming inward. That's mostly on the right side of the Gaussian sphere. And then I've got places where the electric field pierces going outward. That's mostly on the left side of the Gaussian sphere. What's the total flux, though? Did you say 0? You see how we know for sure? Because the total electric flux is merely equal to the total charge inside the Gaussian surface divided by epsilon 0. But what's the total Q inside? I've got 1 microcoulomb and a -1 microcoulomb. 0. Okay? All right. Now I want you to predict. What will be the electric flux to the Gaussian surface if I make the charge of the red particle 0? It's the only change I'm going to make. I'm going to make the charge of the red particle equal to 0. What will be the electric flux? Pause the video, think about it. When you're ready, come back. Well, okay, first let's go in here and change the charge of the red particle by this little drop-down menu to 0 microcoulombs. Notice the electric field vectors changed because now it's only the blue particle that has charge. What are we going to get for the flux? It doesn't calculate it for us. Let's see if we can figure it out. Let me go back to my screen. Let's apply Gauss's law again. Phi electric equals Q enclosed over epsilon 0. What I want to know is that value. Now I have two ways I could try to figure it out. I could do what I call brute force by doing that integral of the electric field over the closed surface. Or I could use Gauss's law, that's the right-hand side, that tells me that the electric flux is equal to the total enclosed charge over epsilon 0. Well, I do not want to do it brute force. You see this over here? It's not that it's incorrect, it's just that it's going to be very difficult to do it that way. Because the electric field vectors E at the different places are not nicely directed. Because my sphere is not at the center of the particle. So let's just do Q over epsilon 0. There's only one Q. It's +1 microcoulomb over epsilon 0. 1.0 times 10 to the -6 coulombs over 8.85 times 10 to the -12 coulomb squared over Newton meter squared. Okay, I'll get some cancellation there. Whoops. 1 coulomb to 1 coulomb. And I'll get Newton meter squared per coulomb. And you put that in your calculator and you'll get 1.13 times 10 to the 5 Newton per coulomb times meter squared. That's the electric flux through that Gaussian surface for that charge configuration, found just by using Gauss's law. Okay? What's the electric flux? Pardon me. What's the electric flux through the Gaussian surface now? Think about it. Pause the video if you need to. Did you say 0? Because now I enclosed the red particle, but it has no charge. So the Q enclosed is 0. Yes, there is a charged particle around, but it's not inside the Gaussian surface. And yes, that charged particle creates electric field everywhere. But for the Gaussian surface, we have that electric field does just as much piercing inward as piercing outward. As measured by flux, the net flux is 0. Okay? Now, if I surround them both again, boom, the electric flux isn't 0 anymore. I could make the red particle positively charged like the blue particle is. I could ask. There we are. They have equal positive charge. What's the electric flux through the Gaussian surface now? It's twice what we had a moment ago, so it's 2.26 times 10 to the 5 Newton meters squared per coulomb. Right? So all we're asking you is how to get the electric flux, or all we're saying is that there's a nice way to get the electric flux if you know Q enclosed. Of course, it goes the other way too. If you know the electric flux, if that's what you know, then it's going to be able to tell you it's going to enable you to figure out what Q enclosed is. Basically, you got Gauss's law. If you know one side, then you can get the other. Okay? All right, so let me go back to my notes here. And there's a little practice I want to do with you. It's right up here. And then we're going to be basically done with this video. Okay. Here's what it says. There is a certain net flux phi sub I through a Gaussian sphere of radius r, and that's enclosing an isolated charged particle. So maybe something that looks like this. Q, and let's draw the Gaussian surface, Gaussian sphere, radius r. I put the charge at the center even though it doesn't say that, because it's just easier to draw. And what we're told is that in that situation, the electric flux through the surface is just some quantity, phi sub I. Okay, now we're going to change the shape of the Gaussian surface, okay? The enclosing Gaussian surface has changed to. And in each case, what we want to know is the net flux through the new Gaussian surface more than, less than, or equal to this value I had, phi sub I. So suppose I exchange my Gaussian sphere of radius little r for a larger Gaussian sphere, maybe something like this. 2, let's say, little r. That's the new Gaussian sphere. What can you tell me about the electric flux now? It's still phi sub I, right? Because we still contain the same amount of charge. Okay. Next Gaussian surface. What if the Gaussian surface is a cube with edge length equal to r? Well, that would be something like this. Okay? I drew it as a square, but you have to think of it as a cube containing the charge Q. What's the electric flux now? Still phi sub I, right? Still contains the charge Q. What if my Gaussian surface is a larger cube with edge length 2r? So now something like this. What's the electric flux now? Still phi sub I. Still got the same amount of charge in it, right? Don't overthink it. Okay? All right, here's the practice that you can do, class engagement on Blackboard. This figure shows 3 situations in which we have a Gaussian cube sitting in an electric field. The arrows and the values indicate the directions of the field lines and the magnitudes in Newton meters squared per coulomb of the flux through the 6 sides of each cube. The lighter arrows are for the hidden faces. For each situation, state whether the cube encloses net positive charge, net negative charge, or 0 net charge. So just to make sure the picture is clear, because it might take a little getting used to, let me talk you through picture 1 to make sure that you understand the picture. You can see you've got a Gaussian cube. Now, of course, a cube has 6 faces. It's only showing me 3, the top, the front, and the right. But there's also a bottom, a back, and a left. All right, this picture right here, like that, is saying that over the top surface, you have outward piercing electric field, and the flux through that surface is 5 Newton meters squared per coulomb. Then over here on the right surface, look at the arrow, you have inward piercing electric flux of magnitude 4 Newton meters squared per coulomb. On the front face, you have outward piercing electric flux, electric field, with magnitude 2 Newton meters squared per coulomb. At the back face, you have inward piercing electric flux with magnitude 3 Newton meters squared per coulomb. The bottom face, you have inward piercing electric flux with magnitude 7 Newton meters squared per coulomb. And lastly, on the right face, you have outward piercing electric flux with magnitude 7 Newton meters squared per coulomb. Okay, with that information, tell me, is inside that cube a total charge that's positive, a total charge that's negative, or a total charge that's 0? And you do that for picture 1, picture 2, and picture 3. Okay? All right, I'm going to share this video with everybody, along with the recording for Monday's class. Heads up, there is another video coming for Wednesday. Watch this one first, and then try your best to see if you can get the next one watched as well, because I need to get just caught up just a little bit, okay? But that's all for this video.